And by the way, I hate to do this to all of you. First period did better. So they were stoic and silent, but they got it done. 60% of them had it done within the first 8 minutes. So we have, and I did a better job in your class. So that hurts my feelings. This is a first principle problem. Net force equals MAC. It's about circular motion. And what is causing the space station to be attracted to the Earth? Well, that's going to be gravity. That is our circular force. And it is causing a centripetal acceleration. Now, that force is the force of gravity between the Earth and the space station. Mass of space station, mass of Earth, g over the separation distance squared. And that has to equal mv squared over the radius of curvature. Now, an important question. What is that mass? Is it the mass of the Earth or the mass of the space station? Wow. You heard it right. A combination of both being thrown out. So we don't know the answer as a collective group. What thing is going around? What thing is moving? Whose velocity are we finding? That's right, space station. Remember, this is the inertial mass, what it's taking to make this thing change direction. Now, that suggests we actually don't need the mass of the space station and never did. You guys who are trying to find the force, that's an extra step. You could be better than this. Now, whatever you didn't know to do to start, why aren't you writing it down? I know who got the answer and who didn't. You should be writing yourself detailed notes of what you have to do to start this problem. Because tomorrow when you're allowed to use your notes on this, they should help you. And I know who should be writing and who shouldn't, if you take my meaning. Now, you should ask yourself another question. It won't come up much this semester, but it will next semester. Are these two r's the same? Is the separation distance also the radius of curvature? I told you how to answer that question yesterday. If the object that's being orbited is very much bigger than what's doing the orbiting, then yes, you can say they're the same. Meaning if the mass at the center is much, much bigger than the space station, then you can cancel out one of those r's. If you can't, they're different r's. But for this semester, you can cancel them out. You should ask that question, though. That makes this relatively straightforward. Multiplying three numbers together and then taking the square root. You do have to find out the actual radius of curvature by adding together the radius of the Earth plus its altitude, or else your answer will be wrong. Now, I'm not going to spend a lot of time on circumstance here. This is how you get 7,664.8 meters per second. I left it in two significant places to make sure that I knew you guys were doing it right when I came by and checked your work. Is this fast? Is this a fast speed? When I ask that question, I don't mean that in a minor way. You should know whether this is fast or slow. You should have an understanding of the size of your answer before you reach it. This is very fast. When you try to think of things that are fast, this beats them all. Speed of sound is 300 meters per second. So the fastest plane using a scramjet engine is about 5 times the speed of sound. And that's still only going to get you around 1,800 meters per second. The only way you can get to these kinds of speeds is to be rocket boosted and to get out of the atmosphere. Now, the SpaceX rocket gets up to this speed in less than 9 minutes with humans on it. So there's no ride in any park that's going to be that exciting. And of course, the Artemis successfully launched this morning at 1:48 a.m. And not only that, it was going much faster than this because it's on its way to the moon. It had to break the Earth's gravity. So it's right now is out of orbit and traveling towards the moon. It's pretty amazing. No. 3 dummies. No people. But it will have its, they're doing lots of missions all at once. So in a month, December 11th, if successful, the Orion spacecraft will touch down in the Pacific Ocean. And they'll have those 3 dummies in it. And they're talking about a manned flight as part of Artemis 2. So it's a pretty aggressive timeline. Your next question could have been done right from here. It's on the board, right? Velocity equals 2 pi r divided by the period. You could find it by just using the velocity you just solved for and finding the period. This answer will be in seconds, though. And, that doesn't mean much. Convert it to something that means something, which is why I divided by 60 to put it in minutes. On the other hand, I think that you should consider deriving it from a first principle. We have this state that we could use and skip finding the velocity altogether. We talked about this yesterday, and the idea of deriving a relationship for the period related to the radius is something I'd like you to be able to do, and I went through it yesterday. I'm reiterating it right now. You can cross-multiply this and get MEG t squared equals 4 pi squared radius cubed. This is deriving a relationship between the period and the radius. Now, that derivation begins here and ends there. But this would give you the period in terms of the given quantities in case you screw something up trying to deal with the velocity. It does have an r cubed in there, and so some of you will have to find that button on your calculator. Or use this and step it through the velocity. It makes no difference to me. But you'll notice I'm not putting any numbers in, because that's also a failing for some of you. During first period,